So let's look at another retrosynthesis reaction for the alkynes. This time starting with the alkyne propyne and being converted into this dialcohol by the end of the sequence. And again, think about what has to happen at some stage and where it's happening. Now, because most of the chemical reactivity is tied up in this carbon-to-carbon triple bond, and the main functionality in our final product is across this carbon-to-carbon bond, which contains the connections to the two alcohol groups. So it's a good bet that the original carbon-to-carbon triple bond on the left is this carbon-to-carbon bond here we see on the right hand side. So the kinds of things which would be having to happen over the course of the reaction would of course be an extension to the molecular skeleton. We've only got 1, 2, 3 carbons, 1, 2, 3, and the final molecule has been extended by another 1, 2, 3, 4. So some form of base like sodium amide or diisopropyl amide with the appropriate alkyl bromide like bromobutane could extend the length of the molecule. That has to happen at some point. Probably one of the early reaction steps, to be honest. We also need to produce these oxygens on adjacent carbons, and we know of two main methods for producing a dialcohol. We could go through reaction of the alkene with a peroxy acid in acidic conditions, making the epoxide initially with the peroxy acid, and then using acid conditions to protonate and open up to the dialcohol with the help of some water. Or we could use osmonium tetroxide with some sodium hydrogen sulfite in a second step to produce that dialcohol. No real choice to be made between either of the two. Either two steps will be fine. If we use the peroxy acid, of course, it would be a trans configuration for the dialcohol. If we use the osmonium tetroxide, that would produce the cis conformation for the alcohol. Although our final product does have that open carbon-to-carbon single bond, so it's really not going to make any difference at all, as long as we use one of them. And we'd also need at some point hydrogenation of that alkyne carefully down into the alkene, so we could carry out the oxidation process, whichever one we fancy. So looking at our overall reaction and starting at the end, of course, with our final product, that would be the dialcohol. We could produce that dialcohol in one of two ways, and I just happen to have chosen the osmonium tetroxide in sodium hydrogen sulfite as our method, because that would have been starting with the alkene being converted into the dialcohol product. That the alkene could have been formed by a reduction reaction with hydrogen using palladium charcoal as a catalyst, ground onto the surface of calcium carbonate, so we produce a cis conformation. And from there, the previous step would have been, of course, making the reduction happen and then extending the original molecule with sodium amide as a base to strip off a proton, and then reacting with the bromobutane, and we extend the molecule and complete our retrosynthesis.